All right, so what we have here next is going to be our memory allocation strategies. Memory allocation as it pertains to keeping track of objects on the heap. So, right, objects will come and go, as we've seen in the garbage collection, right? So memory allocation has a few different strategies. We have 3 strategies to look at: first fit, best fit, and worst fit. First fit is going to allocate the resource request first available block of memory that is large enough to service the request. Best fit. I'm going to allocate memory using the block that is the smallest of the largest. Let me rephrase: smallest of those blocks large enough to fulfill the request. Worst fit, allocate the storage to the largest available block of memory. Okay, so let's say we have our available memory blocks. Some arbitrary size, what doesn't much matter. And then a big old megabyte, the last. So we have a request that comes in for 50 bytes. First fit, I'm going to use block 100. Best fit is going to use block 100. And all the blocks are large enough to manage the memory request. And that is the smallest of those. Worst fit is going to use block 1 million. All right, so in this case, that 100 block would be cut in half down to be a 50 unit block available for additional requests using best fit or worst fit. In the case of our first fit, best fit, rather, in the case of worst fit, this very large block gets smaller. All right, so going back to the original state, request for 150 bytes. First fit, we use block 150. And my example of things are lining up because I happen to create an ascending list of values. So the same block is being used for both best fit and first fit in this particular example, and then worst fit uses block 1 million. Let's do it again with different blocks in a slightly different order. So we'll go 200, 150, 150, 100 again, 350, and then the big chunk of RAM that's available at the end. Request for 50 bytes. First fit is going to use the 200. Best fit is going to use the 50, and then worst fit uses that 1 million again as before. I have a request for, say, 128 bytes. More likely scenario, since memory allocations are going to have a base 2 signature. First fit, still use the 200, right? That block goes down to 72 bytes in size. Best fit is going to use our 150, takes that block down to, what do we got there, 22 bytes in size, and then worst fit, again, takes the largest block. Okay, it's maybe a little larger request we got here. 1,024. Right, all three use the 1 million block. All right, so as a reminder, the way that we get to the state garbage collection, either managed directly by us calling the delete keyword or by a garbage collector running in the background. Everything starts pretty much with first fit, because initially we'll have our 1024, whatever, something like that, bytes available. In the beginning, or any trash is collected, whichever way it was collected, all requests keep chewing away at that one large block. As memory frees up, and we have more options on how to handle which block to use. It's a first fit, very straightforward approach. We just iterate down the free list and take the first available location large enough. Best fit. Since we have the additional criteria, just iterating down a list can be improved upon. Maintain that as a sorted list and use a binary search, looking for the value, the perfect fit. If not finding it, then we'll look at the positions to either side of where perfect fit would have been. Problem with best fit is we can get to a situation where we have a large number of small fragments of memory, right? Such as may block 64 bytes in size and using 56 bytes of it, 8 bytes doesn't afford very much space. Worst fit. This one is the fastest. as all we have to do is keep track of that large block, which basically just advances as we allocate. So there isn't any searching that needs to be done. Just keep pulling away from that. The downside that we have here is that large allocations may soon run into problems. All right, these are the basic strategies. Eventually the real world will come along and we'll tinker and fine tune to better address the situation, right? If we have a bunch of little chunks, it may become beneficial just to ignore them because the crumbs are too small. You just wipe them off onto the ground instead of grabbing the chunk of cheesecake, whatever it is that you dropped on your shirt, and eating the chunk. And just brush off the crumbs. It's not worth the effort to go after those little crumbs. Other things that can also be done is keep track of multiple free lists where you have your list of small blocks, a list of medium blocks, and a list of large blocks. By doing that, you can eliminate large swaths of the data that you need to go ahead and process from that point. Pretty much all there is to these memory allocation strategies. We'll do some exercises later. Let's see. Any questions about this one for the moment? Everyone's good for the moment. Okay. Fragmentation. Fragmentation is separation of memory in one of many possible ways. External fragmentation this is when we have free space between allocated blocks memory, which is basically what we were just talking about with our first fit and best fit. As we get external fragmentation, we try to deal with it as we can. All right, so it occurs, I'm deleting from the heap by deleting from the heap. And be clear, we're talking about the runtime heap area of RAM, not the tree data structure. Right, either directly or by garbage collection. We have internal fragmentation. This is wasted space in the data structure. Structure. Memory that, 2 words, 5, that we have allocated, cannot use. All right, so an example, this one, Boolean that takes more than 1 bit of memory. such as a stack location, which is likely taking 32 bits. Arrays often have internal fragmentation, especially character arrays. All right, example, char 10 name equals Bob. All right, we're only actually using 4 characters there. It's memory that we don't get back until we get that, release that particular variable back. All right, hash table. Another example, where we internally fragment the data by design. Lastly, we have, what doesn't like about that? That's fine. We have data fragmentation, where related pieces of data are physically separated. Linked data structures are likely to endure this situation. Okay, so let's allocate some blocks of memory. All right, where's my fill color? All right, so memory allocations, if whatever size, I'll just give them different color regions, represent the different allocations, right? Whichever memory allocation strategy we were using, as we talked about before, is going to follow this initial pattern of just growing the memory footprint. As time goes on, we'll eventually start getting to the point where we will no longer need something, and then we can get that memory back. And so this is just our initial set of whatever objects, quite random. At some point, right, create a fragment, deallocate a block of memory. And now we have the external fragmentation. And the fragmentation can come and go, right? We might get another request to allocate a block. And we might still have external fragmentation going on here. Just depends. Just depends on whatever our allocation strategy is and how things line up, how big the hole was, how big the data request is. This is external fragmentation where we have an empty space in between blocks of allocated memory, and the deallocation will come and go as time goes on. Just depending on what we deallocate will drive. Are we creating more holes, or 2 holes that are adjacent to each other and happen to be collapsing together? One last deallocation. All right, let's go ahead and chew away this burgundy block, whatever color that is. And sometimes two fragments will merge together. It'll be a smart heap allocation strategy to recognize that this isn't two blocks of 4 chunks, but rather coalesce them back down to a single block. Kind of like droplets of water, we like those to go ahead and merge together so that it's fewer drops of water to have to keep counting as they fall down to the ground. Some internal examples. Another way go ahead and create a class for a struct. You can see this fragmentation go on here is with some simple types where we can fold things together a little bit differently. And in fact, let me go do this in code so in case it doesn't keep getting mucked up on me. All right. Struct testing 1. Right, num. Oh, I guess I should use the right programming language. It's always helpful. Right, so we've created our testing struct, which is just a wrapper around our short at the moment. And it allocates or requires 2 bytes of memory for any one that we would create. As we grow things, things will also grow. Now, let's pay attention to what our numbers are here. Short was taking 2 bytes, took the same struct and added a char to it. And if you'll recall correctly, a char in C, C++ by default is going to be 1 byte of space. Since we're using the ASCII table, this is a different language, we'll be getting probably the same results anyways, but without the fragmentation that we have right here. So notice 2 plus 1 somehow is managed to equal 4. The reason why that's happening is it's known as a word boundary. You'll learn more about word boundaries in the assembly class, but it's kind of like we have with the page boundary here, right? I have my paragraph going across the page boundary. If this was considered to be one chunk of memory, this one paragraph, it's straddling across 2 page boundaries would be not allowed. It would have to begin at the beginning of a page boundary like we have here by entering a page break. So the crossing of a boundary doesn't work unless the size of that block of memory is actually larger than the word boundary, which we'll see when we get into doubles and things like that. Assuming a 32-bit system, our word boundary is going to be every 4 bytes. So what I can do is come along here and add a second letter. And that'd be testing 3. And we'll have testing 3 also be 4 bytes. And run that because there is still room for it. Right? And there's 2 plus 1 plus 1 is 4. 4 is within space. We're good to go. This is one of the things you want to pay a little bit of attention to when you're doing your class or struct design with your primitive types, right? Pointer types doesn't matter too much. With your primitive types, if you're not paying attention very closely to the order, you can start causing unnecessary bloat here. All right, so I'm not even going to change the definition of testing for. It's still letter 1 and num in it, but I am going to change the order. Look at that, I have a bug there. Let me go back and show the 4 again. There's the 4, even though I had a copy paste bug. All right, now on the testing for. 1 plus 1 plus 2 should equal 4. However, that word boundary thing is going to come into play here. And we see now it's taking up 6. All right, so that char is taking 2. This one's taking 4, and this one's taking 2. Really, this letter's only taking 1, but there's that spacing here, and actually, the word boundary in this particular machine is much smaller than I was expecting to see. So on that thread, I'm going to pop this over to, I already have this open. So let's random code, jump over to our data structures, language. There we are. All right, run it over here. Same code, different platform, most likely. Oh, that's right. Darn it. I managed to corrupt my installation. Doing some green a while back, I managed to have a framework code file open, and I totally saved someone's lab on top of it, and I lost that. So I can actually demonstrate. You know, maybe I can demonstrate the older version. Let's go through a different version of Visual Studio. Let's see if I can't do it over here. Yeah, let's create one. Plus empty, good. Here's for some hope that's actually using. Try hope again. If I click the right button, see if we can get things to compile.
Are you trying to show us a file? Because I can't see anything.
I'm sharing my screen.
Oh.
I assume everyone else can see my screen.
Yeah.
Yeah.
Okay.
You can see the online GDB, but you can't see Visual Studio. Interesting. Well, I guess I'll just swing on back to online. Okay, so let's see if testing 5 pops up. Can you see testing 5 struct?
No, Professor.
Nope. All right, looks like I'm frozen in time. Let me stop the share and restart that.
Yeah, I don't see. I know somebody else can see it, but I don't see it.
Uh, I'm stopping the share. Zoom is taking a moment to think about it right here.
I still see online coding.
Yeah, looks like I might have to kill Zoom here. See me not responding. So looks like I'm gonna have to reconnect. So I'll be back in a moment. All right. How's the screen looking? Is it zoomy?
Yeah.
All right. Okay. Well, I had run Visual Studio over here as well. So you see Visual Studio?
Yeah.
Yes.
All right. My numbers ended up being the same as well on that one. So we can swing back to our online compiler now that Zoom is no longer frozen. All right, testing 5. Right, add a double. Big number. Testing 5, testing 5. All right, so goes up by 10. All right, I added 8 bytes, end up going up by 10 bytes. Again, because we have the word boundary. Don't worry too much about word boundaries for the purpose of this course, other than the awareness of that internal fragmentation can happen in the code. And this is gonna be the same thing for whatever language. Go look at. Hey, there's a way. Can I do size of? Yes, I can. Okay. Same thing, different platform. Right here, it's taking 1 byte. Still too much space. At least more space than it's needed. Same story, different day. Oh, that's right. I can't do that in C#. Okay. It's always fun getting your languages crossed. But all the languages still need to go ahead and work on the underlying machine. And the underlying machine wants to have things line up so that they can work on things. Can't have things crossing over in the middle of the threshold. Just realized I didn't bring the chat window back up, so let me go dig that up. In case anyone is saying anything in the chat, since I had to rejoin. Okay. All right, so internal fragmentation. The other area where it's quite prevalent is going to be on disk. Text document, small doc. And we'll just go ahead and edit this with our always fancy notepad. Best editor ever, in no one's opinion. All right, I'll save the file and look at the properties. Zoom that in there a little bit. All right, it likes to lie. Windows is a little bit lazy. It's saying it doesn't have any size on the disk yet. That's going to be a lie, because obviously if it's on the disk, it takes space. It's not a magical bit of data compression going on here just yet. It just hasn't been persisted to disk. All right, let's force the issue and give this file a little bit of magnitude so we can get our fragmentation to show up here. Can I just refresh that? I didn't think so. Let's get the properties. All right, now we actually have some file size. 79.3 kilobytes, actual size on disk. Numbers actually happen to be pretty close together. only less than 700 bytes apart, but the file system wants to do the same thing. There's a smallest unit of measure that the disk wants to use for a file. See if I can shrink this down some, because it wants things to start on the edges because it's too difficult to try to track things when they're not the edge, right? So I made my file quote unquote smaller by 4 kilobytes or thereabouts, but the actual file size on disk unchanged, because all I do is give her some space at the end, right? Because remember, files are arrays, effectively. Arrays of bytes on disk. You might treat those bytes as character data, or might just treat those bytes as byte data. If it's a binary format, image, application, something along those lines. But the internal fragmentation is going to be present here as well. Okay, let's see if I can find my window. Not over there. I'm going to do this, just do Alt Tab. Nope, all right. It's always fun when things disappear. Okay, fine. Just get another window going. Any questions about internal fragmentation at the moment? Okay. Let's see, where's my online? There, okay. I have a code file like this. In the files section, same idea, just different structures. Let's try it again. But it's going to be the same idea. Wasted space on the inside, right? Even the double is going to be doing it, especially if you say something like double x equals 2.5. Right? We need about 3 bits to actually represent 2.5. If we could really compress the heck out of it, but most of the bits in this representation are going to be unused, right? If we go look at programmer, and decimal is fine, right? 12, right? The binary for that 1100, but if I used a double to store this, you can see it here's mentioned the words as well. We're not going to get into that. Right, a double is 64 bits, and we only needed 4 of those bits to actually represent our value 12, which is probably not the best example because floating points. So 12.5. If it's going to let me, it doesn't give it. Okay. Let's see. What can we do here? It's fine. Right. Even our ints, right? When I say int count equals 10, right? Int goes up to plus or minus 2 billion. So there's gonna be a whole bunch of bits in there that we're wasting space on. When we talk about some memory compression techniques, we're going to recognize that wasted space, that internal fragmentation within inside our data representation, and see what we can do to save some of that in our data storage. And so data fragmentation. Here, if I create a tree object, There's a tree. And then I have graph. And then I just have a loop. And we just go ahead and build up. Call some add function. Call some add function. All right, 25 times. If we go ahead and, excuse me, build out our table. And let's say a tree node. We have a four byte data pointer, and we'll do 3 blocks. See, each of these blocks is 4 bytes. All right, so we come along and we create a tree node. And let's say our graph node is probably gonna be around the same size. Maybe it's a little bit smaller. We'll make it smaller so it stands out as different. And then we create our graph node. And then we create a tree node. And then we create a graph node. We create a tree node, create a graph node. And that worked out. And we keep creating. It's all these red blocks, memory that are allocated. Sorry, are related to each other. And the same thing with all the yellow blocks, right? These are all part of the graph. Adjacency list. In this particular case, we're talking about an adjacency list graph. Thus the dynamic components. If this was in a matrix, right, the graph would have to be one big massive chunk. So when create these 2 objects up, tree pointer would be a little bit of tiny space, but then the graph reference, it's a 10 by 10 of integers. We're talking about our 100 times 4 bytes, 400 bytes of one contiguous chunk of memory, because that's how an array wants to be, assuming it's actually one contiguous array. If it's dynamically sized matrix where it's actually a jagged array, each of those 10 arrays are then separate arrays, and those arrays might be separate in memory depending on what's also happening in the system at that point in time. All right, so we have these lovely fragments where related data parts are split apart. You get the same thing. File system. Do the same thing with large files. Just filling disk and breaking the file apart. If there is already a large free chunk on disk, we can get around that. But if the disk is fragmented, then we have to split the file. How are we doing here with data fragmentation? Or any of the fragmentations? Chat's so quiet. Did the chat break as well? Meh. All right. Meh's better than no answer. All right. In an ideal world, ideally, there is no data fragmentation or external fragmentation. Studying is always recommended. We can attempt to address this with compaction. Something that a garbage collector may have at its disposal. I guess the pun was slightly intended because I thought it and then recognized it and still typed it anyways. External fragmentation can just shift memory over, collapse the holes. This does help with our locality of reference, as well as make large allocations have a better chance of succeeding. We do have to be careful here. I'd say we're going to kill the graph. Say we say delete graph. All right, that is going to cause fragmentation of the external variety. And I'm going to go ahead and add some labels here so we can track nodes. A, C, C, etc. Just work my way through the alphabet. Try to work my way through the alphabet. I guess we're going to skip a letter. Why not? It happens. Sometimes the letter gets left behind. Not enough room for the entire alphabet. This small example. Okay. All right, this is a tree. It's a linked based structure. So A is probably the root of the tree. It's the first one that came along. It's pointing to B or pointing to B and C, depending on, is it a binary, a ternary, however many degrees it is, but we are pointing to them. I cannot just collapse the memory as is. Let's see, I did it 3 times. So I'll go ahead and insert. We can't just straight out collapse. I'll get there. 8, 4, 8. Just jostle everything around here and be good with that. Because now all my pointers are broken. All right, we just collapse. I have pointers pointing to the wrong place or a place that no longer holds nodes. All right, A was pointing presumably to this chunk of memory where B was before, and this chunk of memory over here where C was before. Now, that's not our object there. If we try to get into those objects, things fall down. You may have heard the term dangling pointer. Dangling pointer is somewhat similar issue here. Dangling pointer is a pointer that was pointing to a location in memory that used to be something at a point in time, but then someone came along and did say delete, but they didn't null the pointer that was pointing to that object. And thus it was pointing as a leftover as a dangling thread, basically. And then you get all kinds of fun, weird runtime behavior there because it tries to treat that memory as though it were a node, even though it might just be a book, a car, a train, automobile, plane, whatever. might happen to be there in memory. Right, so that's also what the garbage collector is going to have to manage. If it does the compaction, the pointers that are inside of this object need to be reset to wherever it is we move things around. So we just thank you. Hopefully I got the mic far enough away that I didn't pop some eardrums. All right, so in order to do the compaction, it involves moving objects around in memory. Means we have to be able to update pointers to where things are being moved to from the compaction, which means we have to understand the type system, the garbage collector, or the memory manager that's trying to do the compaction has to fully understand this data type. It has to know what our tree node data type is. So we come along, create a class called tree node and give it 2, 3, 5 pointers. The application has to know what's a pointer, what's not a pointer, so we can go ahead and update those things. And that was actually a similar concern that we had with garbage collection. When we were tracing through the objects, if the garbage collector didn't fully understand the object definitions, what's a pointer versus what's just regular integer, because 4 bytes of memory versus 4 bytes of memory, there's nothing intrinsically different between 2 different chunks of 4 bytes of memory. It's the type system that we're putting around there. Would I type it as an int star or just an int? Because the behavior of an int star, even though it is largely similar to an int and is going to be referring to a location memory where we'll find an int, is a very, very different beast, substantially different. Value type versus reference type is a huge, very divide between those 2 data types. Right, so things like .NET, Java, they have built-in garbage collectors. They understand the type system, right? Whatever data type that you create, they can reflect and understand what is reference type, what's not reference type, and go along from there. Yeah, now is a good time for a 5-minute break. It's been almost an hour. So yes, let's take 5 minutes and then we'll go ahead and come back and talk about the test. So we can go ahead and stop the recording now.